conditions like superposition and linear proportionality. These are two very important properties. If you flunk any even one point does not satisfy that, theoretically, then it's nonlinear. But it could be very near linear. Yeah. And we don't have this definition to give that. So what we need for the stationarity, in addition to a qualitative answer, we should look for a quantitative answer. Yeah. A quantitative answer is that it's going to give us, say, how nonlinear or how non-stationary it is. Yeah. This is the look for a degree of stationarity. So if you look at the definition of stationarity, the definition of stationarity is very strict. That means for any random variable, the random variable, if this square of this is less than infinity, and it also has a mean, this is very important. It has to have a mean, yeah. And for non-stationary process, the mean does not really make any sense, yeah. Like yesterday, last time I explained a function that sits on a slope. If you take a wave and you take the mean really does not give you any information about the wave because of the trend that is sitting on. So having mean is important here. In most of the probabilistic study of random variable, the assumption is stationary because it's looked for global property. The global property means the whole population has to have the same characteristic, and that implies stationarity. Now, we have this less than infinity, that means finite, and we also have this have a mean. In addition to that, the joint probability distribution of 1 to n is the same as the joint probability of 1 to n shifted any arbitrary tau. Any tau. You can shift it 1 step or 100 steps. If you, in other words, if you randomly selected the n points, and then you shift the pattern, any arbitrary steps, and the distribution is the same, the probability structure is the same, then that means stationary. Yeah. Anybody has checked that? I have never. Because it's to check for all tau, it's not possible. Yeah. Even for finite data, it's not easy to implement. So this is the definition. Because the definition is so restrictive and so rigorous, mathematicians always make the definition very rigorous. So it does not, people ignore it instead of do it. So then they modify that. They modify to what is called the wide sense stationarity. We still have to have this finite. We still have to have a mean. But instead of a joint probability of n points, we now take a joint probability, just autocorrelation. Just take tau 1 plus T1 and T2, and T1 plus tau, T2 plus tau. If this correlation or distribution are the same, then we say this in wide sense stationary. When this and the distribution of this and distribution of that are the same, that means the autocorrelation only depends upon the time separation. The 2 points time separate. If it's the fixed, then it's everywhere it's the same. So the time autocorrelation function is the same. Now, if you have autocorrelation function the same, then that implies the spectrum is the same. Because Wiener-Crunchin theory says that the spectrum actually is the Fourier transformation of the autocorrelation. If autocorrelation is identical, and it only depends upon the time separation, then the Fourier spectrum is identical. Then, in addition to that, we also have a statistic stationary. Statistic stationary means that if we carry out an average process, yeah, we take one section, we average it, and take the next section, average. If these two, after averaging, is the same, then we say this is stationary. Yeah. Now, all averaging involves a time scale. So you have to know that the definition of this is how long a time scale you're averaging. Yeah. Like, for example, white noise. White noise is regarded as statistically stationary, because if you take a long enough section, you average it, then it's all zero. Yeah. If you do a probability, it's all the same. It's all white. Yeah. The spectrums are white. So white noise, even though it's randomly varying, it's regarded as a statistically stationary. Yeah. So there are all kinds of definition of stationarity, but most of the definitions, as I said, are so restrictive that people don't use it. It's never really checked it. So here, I define a degree of stationarity. So in the past, to define degree of stationarity is not easy. How you define, how to do it. Yeah. So in this way, what I did here is that the first you have to have a very good time frequency distribution. You know the distribution is function of frequency, and not only frequency but also function of time. Yeah. Like for example, the spectrogram that I show you at the beginning, and that is not a function of time. So then it's stationary. It's only frequency. Therefore, whether you look at it as a time frequency distribution or only as a frequency distribution doesn't make any difference because any time is the same. So here, for time frequency distribution, the h omega t, if we integrate this omega t with respect to t and integrate it from actually 0 to capital T and divided by capital T, then this then becomes independent of the time. Yeah. So this averaging has no time involved. Yeah. And if our spectrum has no time involved at the beginning, so then everywhere it's NT. So what we have is that we define this quantity to measure degree of stationarity. The degree of stationarity actually is, in fact, it's n minus ht over nt over n. Yeah, n over n minus ht means the difference of the local spectral density to the mean value. If everywhere the value equals to the mean, then this integral will be 0. Yeah. If somewhere it's different, then it's not 0. So this actually gives you almost a percentage of degree stationarity. Now you can call this percent. Yeah. Even though I did not call this percent, but the quantity eventually comes out, it's actually a percentile, average as a percentile value. But the one difference between the percentile quantity is that this value could be more than 100%. Yeah. Usually when percentile, you normalize it, will be less than the less than 1. But here, it could be more than 1. Yeah, because this ht is highly variable. The ht could be higher than that. So 1 minus this may not be always strictly less than 1. As we said, this is a degree of stationarity. But many problems, if you check degree of stationarity, it will not satisfy the stationarity condition. But if you enlarge it to statistical stationarity, that means if I average over a certain section, then it still could be stationary. So again, we can use this kind of thinking and define degree of stationarity. The degree of stationarity is the same that we define this average. Then we take the average of the spectrum over certain time period. If this come out to be constant, then we regard this as a statistically stationary. Yeah. So here I define two definitions of stationarity. The one is degree of stationarity. The other one is statistical stationarity. Degree of statistical stationarity involves another time scale. You have to know how long you average. Otherwise, it still could be non-stationary. So as an example, here it's an example of water wave. Water waves are nonlinear, and the crest may break and may need harmonics. So the waves are also non-stationary because the wave come in groups, and not only come in groups, the wave can be generating process or decay process. So the wave is changing all the time. This is a section of water wave that we measured near the coast, near Norfolk, using a station. You can see that this has a general slope coming down. This is not because the sea level is changing. This station is near the coast. It has tide. Yeah, the tide is going down. So the mean water level is going down. Yeah, that's the tidal station. And this whole station covered 60 minutes in 1 hour. So in 1 hour, you measure the sea surface. The sea surface, the tide level is started changing. And we can decompose this using EMD and eventually plot out a Hilbert spectrum. Yeah. This Hilbert spectrum I have smoothed 3 times using 9x9. If I do not use smoothing, it will look very spotty. It's very dots here, dots there. You cannot even see the energy. And roughly, you see that the higher energy is either blue or purple. And you see that this area are the main energy. Most of the energy actually is confined in this region. Yeah, and this region is roughly 0.1 hertz. 0.1 hertz means 10 seconds. And the water wave in the ocean are generated by wind, and the average wind, the generated waves, roughly around 10 meters per second. Yeah, 10 meters per second will give you about 10 seconds wave. So if you go out in the ocean, the water wave, roughly 10 seconds. Not only that, wave comes in group. So roughly every 7 wave, it's a big one. So when you do surfing, you can count 1, 2, 3. You skip 6, and then you catch the 7th. Most likely it will be a large wave. Yeah. So these are the empirical facts. So if you smooth it more, you see this energy concentration even more clear. And if you do not smooth, you will never see it. Yeah. But if you average over the spectrum, average over 100 steps, sorry, this is average over 10 steps. Every 10 steps you average. This is over 100 steps you average. Now you start to see a more horizontal structure versus at the beginning, it's a more vertical structure. So they are very different. So if it's vertical, it from one time to another time, it definitely is different. Therefore, it's non-stationary, and it becomes a little bit more horizontal, and eventually, instead of vertical structure, everything becomes horizontal. That means that after 100 seconds average, you will start to see that we do have some stationary places. So then this means this process becomes almost statistically stationary. Yeah. Then the spectrum looks like this. This is the wave spectrum. We have a very sharp peak at around 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ Yeah. The first one is degree of stationarity. This is 10. This is 1. This is 1. That means most of the wave, actually, if you compute the degree of stationarity, it's highly non-stationary. It's really not simply simply 0 or whatever. The degree of stationarity is not 0. But if you average 10 times, 10 steps, the degree of stationarity dropped. This is statistical degree of stationarity. Now it becomes pretty much near 1. And then if you average 100 steps, then it dropped below 1. Most of the value below 1. This is 1/10. So the degree of stationarity is it's pretty stationary, maybe 10% non-stationary. Yeah. So this is 0.1. So it's 0.1. It's 10%. So from a very non-stationary process, if you average and average, eventually you can make it stationary because you averaged it so long. Yeah. So statistically, it could be stationary. Yeah. Another example is earthquake. And if you look, earthquake is definitely transient because earthquake come and then immediately disappeared. And if seldomly you have an earthquake continuous for more than a couple minutes. Yeah. So especially in the near field, the earthquakes are highly nonlinear. So traditional treatment of earthquake is again almost treated as a stationary process. But the earthquake community, however, if you ask them, they say, no, we have never made the stationarity assumption. Earthquake people, when they talk about earthquake spectrum, they don't admit they use Fourier spectrum. They say they use response spectrum, the response spectrum. What is a response spectrum? So response spectrum is you get the earthquake signal. You use the earthquake signal to excite a system of 1 degree of freedom system. This 1 degree of freedom has a different frequency response, different stiffness. So for example, this degree of freedom is 1 Hertz. Then you use that to excite, you plot out the response. And you take the maximum value, and you take another one, it's 1.1 Hertz. You excite, you plot out the maximum. Each of the maximum correspond to each frequency. You put the dot over there. That is eventually the response spectrum. The response spectrum turns out is exactly the Fourier spectrum. Because the response spectrum is that you take you take the linear single degree freedom system with with predetermined damping, and then you use the earthquake signal to drive the system. So here, A is the earthquake acceleration, yeah, and omega is the undamped character. This omega n is the frequency of the system, and then this C is the damping factor, and then this omega d is the damped system frequency. So use this system and drive it at the one particular frequency. Yeah. And using that particular frequency to determine the frequency response of the spectrum. This, actually, this, if we set C equal to 0, this is nothing but the amplitude of the frequency do a Hilbert transformation, do a Fourier transformation, sine transformation. Yeah. So this spectrum is nothing but Fourier spectrum. Yeah. This, the way you write out this form, this is called the Duhamel integral. Yeah. It's the simple way to solve 1 degree freedom system. Yeah. This is Duhamel integral give you the response spectrum. So response spectrum is indeed a Fourier spectrum. The reason that it's a Fourier spectrum is that this response has a known frequency. In other words, the system that you're driving is a linear filter. Each one is set at one frequency, and it only look for that particular frequency. So that's why the Fourier integral of the response spectrum computation give you exactly the Fourier spectrum. So the response spectrum and the acceleration response spectrum and the real spectrum, the only difference is one factor of the frequency. So you can recover the frequency spectrum or Fourier spectrum very easily from the response spectrum. The Duhamel integral actually gives you a quantity of the dimension of velocity. And so the response spectrum is known as the pseudo-velocity spectrum. Why it's velocity spectrum is because of the difference of this omega frequency. So linear 1 degree system is a linear filter. So the relationship between response spectrum and the Fourier spectrum is really 1-to-1. It's very easy. Here we have 3 earthquake record. This earthquake record I got from a Jiji earthquake. That is in 1999. It's exactly 10 years ago. We just had the memorial service or celebration anniversary, 10-year anniversary of Jiji earthquake. This station turns out it's has the largest acceleration. The largest acceleration is here. It's almost 980, which is 1G. I got this data without description, and later in some symposium, people started to discuss this station. They say that this station actually is damaged, and because of the damage, the instrument has a free fall. When it's free fall, the vertical, this is vertical, this is a, no, I'm sorry. This is a east-west, and this is a north-south. This is vertical, yeah. So this has a acceleration of 980. That means that it actually has a almost free fall. But amazingly, free fall does not appear in the vertical. That's strange, yeah. So this is the largest acceleration that I have ever seen. Yeah. And if you do a spectrum, east-west component, you see that this Fourier power spectrum looks like this, and this is a response spectrum. They look very much the same, almost even agree in detail, not only in shape but in detail. So the response spectrum is nothing but the Fourier spectrum. This is east-west. This is north-south. Yeah, north-south. It's also the same. The Fourier spectrum, you cannot have frequency very in detail over here because of the sampling rate. The response spectrum, you can put frequency at any place and still compute the frequency. So usually when you compute the response spectrum, you distribute this point evenly. So it's not like a Fourier has lots of point here, less point here. So response spectrum, you can have uniformly distributed frequency spot. So this is north-south. They are, again, the same. And this is the z direction, the vertical. So I plot this not because they are valuable. I just want to show that the response spectrum is indeed the Fourier spectrum. Yeah. In fact, when the response spectrum was first introduced, people try very hard to claim that this is a Fourier spectrum. But later, of course, they don't want to say that because they find that the Fourier spectrum is only working for stationary process. So they try to justify it. So even though it's non-stationary, response spectrum is the work of actual signal, so it should be right. But turns out the work of actual signal is based on a 1 degree freedom system, so it doesn't matter. This is the earthquake Hilbert spectrum. The Hilbert spectrum is that here, when the earthquake first starts, you have some very high frequency wave, and it propagates much faster. And this is the compression wave. Yeah. And then after that, these shear waves start to come in. So this wave typically are high frequency, and the compressed wave usually are not very high amplitude, but it propagates much faster than the shear selection. But the shear wave actually causes most of the damage over here. It's much lower frequency. Another thing you have to know is that the high frequency wave, by high frequency, it's come to, for example, 10 hertz, 15 hertz, almost between 15 and 20 hertz. When the frequency is so high, the building does not respond to the earthquake waves, because like a building like this, it does not shake as fast as 10 hertz. Each second shake 10 times. It will not respond to that. Typically, a 10-story building will respond to 0.1 hertz wave. It's every 10-story, 1 second. Yeah. So 10-story wave will respond to 1 hertz wave. As instead of 10, we come down to here. Yeah. So lower frequency, it's much more damaging. And if you go to taller building, like 101, it will respond to even longer wave. Yeah, even lower frequency. It's about 10-second wave. I was told by Su Zhengzong, one of the, did Su Zhengzong show up in here when Zhang Jianzong gave the operation? Yeah. Mr. Su worked in the at the Central Weather Bureau. He's in charge of the earthquake monitor in the whole Taiwan island. Yeah. And there are many seismometers actually installed on the building. And one of the stations is very interesting is the building 101. Yeah. And he showed me some very interesting data. The data is after Wenchuan earthquake. Wenchuan earthquakes 2 years ago in Sichuan has the largest earthquake that killed 100,000 people. 好几万人, 十几万人 died. After that earthquake, the people at 101 get seasick because the earthquake eventually appeared and it moved the 101 like at 0.1 hertz. Yeah, 0.1 hertz means exactly like the ship rocking in the ocean, and it lasts for a whole afternoon, a couple hours at least. So many people feel sick over there because of the motion sickness. Yeah. So the earthquake signal and the extremely low frequency components are important for tall building. But like 101, the building taller than 30, 40 story, the earthquake is no longer the most important force anymore because it does not respond to high frequency, which most of the earthquake energy is over here. So the tall building, it's not, the earthquake is not the main threat. The main threat for the tall building is actually wind. Most of the tall building are actually designed according to the wind. The earthquake moved the ground. So the tall building stand there, it just moves the ground like this. Yeah. So the whole building will move. So the force is less. But if you have wind, it actually is a cantilever beam. You bend the building, and that is very stressful. So for 101, the building like that is actually the design factor is wind. Long bridges are also designed according to wind, not according to the traffic is of course important, but traffic compared to wind force, especially in Taiwan, the wind force is not that critical. Taiwan does not have a very large bridge. Yeah. If we have a bridge like the Golden Gate here, then we'll have a problem for each time a typhoon comes around. That would be serious. Yeah. In the United States, there was one bridge built in Tacoma Narrow in the 30s, and after they built, actually it's collapsed in a storm. Yeah, the bridge vibrates so much it just resonance and collapsed. Yeah. So this is the earthquake Hilbert spectrum. You can see how the time change. This is the north-south component. Again, we have the compression wave. This is the vertical. The compression wave does not generate vertical component because you compress the soil. So you have vibration, but the compressed wave it's no longer visible. And even shear wave, it still does not generate high enough vertical motion. So when you compare the original data, you will see that this is actually very, very low in magnitude compared to that. So when you compare this spectrum with the Fourier spectrum with Hilbert spectrum, they are different. But it turns out this spectrum that I compare with, this is actually amplitude spectrum, which tends to emphasize the lower frequency. So this comparison, later I found out it's not really that fair. But nevertheless, we do emphasize the lower frequency. This is north-south, and this is a Z component. If we average the previous spectrum, looks like this, the east-west. If we average 200 steps, you see the vertical structure now becomes horizontal. In other words, now here, now it becomes more stationary. So all of this is to try to tell you non-stationarity has a degree. Not only has a degree, if you average it as a statistically non-stationarity. And if you average 1,000 steps, it becomes really horizontal. So by this time, you can almost compare it with the spectrogram. If you plot the spectrogram, it probably looks like these little steps. Yeah. So spectrogram actually give you a statistically stationarity measurements of this. And this is 1,000. So this is the spectrum. This is the degree of stationarity. It's definitely not stationary. Not only definitely not stationary, the higher frequency one, it's more non-stationary. The higher frequency one vary a lot. And if you average the 200 steps, it becomes almost 1. It average 1,000 steps, it's much less than 1, but it's still not like the water wave. The water wave is much more stationary than the earthquake. Yeah. Indeed, the earthquake is more transient than water wave. Water wave keep coming, but earthquake does not. So you can see that the degree of stationarity actually give you this indication. This is north-south. It's the same trend. Degree of stationarity, and this is a statistical degree of stationarity. And this is the vertical. The vertical, no matter how hard you average, even for 1,000 steps average, you still have almost 80–90% non-stationarity. So the earthquake data, we definitely should not look at its spectrum for anything even remotely related to the Fourier spectrum. Yeah. So this is the degree of stationarity. You can see that the z direction is much more stationary than the east-south or north-west, and that you can almost see that from the data. This is much more stationary than that. Yeah. So the degree of stationarity actually prove that. This is a degree of stationarity. East, west, north, south is all behave similarly, but vertical it's different. And here it's for 200 steps, the degree of stationarity for vertical is still low, and this is 1,000 step average. This is 1. So now this is about 60 or 70% stationary for this earthquake. So Hilbert spectrum analysis reveal a damaging causing low frequency band of energy. Yeah, the strongest component east-west is also the most non-stationary one, and the weakest component Z is the most stationary one. And Hilbert and Fourier agrees well for the stationary case, like the vertical case. It agrees the best. Yeah. This one, yes, heart rate variability. Let me see. Let me see whether most people here are not really interested in heart rate, right? Let's see whether I should cover this or jump to a new. I think I will skip the heart rate. I would start a new new topic. Let's see this. Okay, we'll change the subject. Because the semester is too short, I have to cover this. Now we talk about the Hilbert spectrum for time series. Now many people ask, how about the two-dimensional image, or even three-dimensional body? A body has a different density. Can we do spectral analysis of those cases? So the first one is called the bidirectional spectral analysis. This is actually for image, because at the beginning, after people have seen Hilbert transformation, immediately they want to do image analysis. So this is a generalized EMD to do 2D case. To do 2D, this is a very troublesome thing. First is how to identify the extrema in 2D. In 1D, it's very easy. I take a point, I compare to my neighbors. If I'm bigger than both, I'm maximum. If I'm smaller than both, I'm minimum. 2D, it's not that easy because you have more than 2 neighbors. You have actually at least 4 neighbors. It's conjunction next to you. And actually, you should compare to more than that. You should compare to 8 for different direction. And so this immediately creates a problem for saddle point. For saddle point, there are many saddle points. Saddle point is not a singularity in 2D. Any times you have maximum, minimum, and you have a ridge, and you have a ridge in another direction, you have a saddle. And saddle point, it's your minimum in one direction, maximum in the other direction. So that's created a problem for how you define extrema. And also ridge and valleys. Ridge means that in one direction you are not. You are in the slope. In the other direction you have maximum. The reverse side is valley. So this create a problem for looking for maximum, and you create a surface. A minimum, you create another surface. This surface, how you handle saddle point. When you have a saddle point, then you have maximum, minimum, you have a hard time to define. Not only that, even after you create all the point of the extrema, it's difficult to generate a spline surface. There are various methods to construct a spline surface. You can have a radial-based function and many different ways to create the 2D. The third is how to fix the edge. The edge, in 1D problem, 1D spline, we have problem for edge effects. For 2D, the edge effect is even worse because they have all around you has the edge effects. So the general problem for bidirectional, it's pretty difficult. And the basic idea is that if you have a surface and then you create the top, you use the maximum if by lock and by hook and by crook, and you can defined. You put a surface up and surface down, then you can create a mean surface. This is the basic idea. But the basic idea is hard to implement. Yeah. And one of the difficulty, for example, is how stiff is this surface. If the surface is very hard, it doesn't bend that easily. Yeah. So how many small extrema you have to come down to meet? If this surface is very flexible, then once you screw it on, it will sag and touch every maximum. Yeah. But the flexibility is one of the choice that you can make. Yeah. So that's when you determine the surface. So these are the ways that has been tried. One is radial base function. The other one is thin plate. Thin plate means I put a plate, I put it on the surface, and surface has a finite number of support. If my plate is stiff enough, then only I touch the high spots. And if plate is flexible enough, I touch more and more. Yeah. So, and another one is Delaunay triangulation. That is, I identify all the extrema. I connect all the extrema by triangle, and I create a surface. But this surface consists of triangle, so it's not a smooth surface. That creates some problem. And another one is by slice. So instead of put a whole surface, I cut my picture into little slice, and each slice I can analyze it as a function of as one-directional data. Yeah. The final one is non-uniform rational B-spline. This is the design principle for most of, say, like a car or a boat or whatever. The problem for that is they just say, okay, you have some control point. I will go through certain control point, but I will give you a smooth surface. I do not pass through all the points. So radial base function is the first one. The radial base function is that if I have n number of set of points, the radial base function approximation is that I will find a low degree polynomial, typically linear or cubic or whatever. Many people still use cubic. Yeah. I use this cubic function to fit these points. In between is x. I fit this point. And then they multiply this by lambda. Because I fit this function, I look for this lambda coefficient to be a best fit. Yeah. And and all these functions are real based a real value function called the basis function. And so you use, for each point you pick, you fit to its neighbor. How many neighbors you have? N neighbor. So you try to fit every neighbor to determine this lambda. So lambda, how many points you get, it's the number of control points determine the number of equations. And once you get that equation, you solve the joint equation to get the coefficient. So this is a very, very time-consuming thing. If I have a 1,000 by 1,000 image, and say I have 100 extremas, then I have to solve a system of 100 joint equations. Yeah. So this is a radial base function. For this base function, I can choose any of this function, whatever function you can select. You can select a linear, you can select a cubic, you can select a logarithmic, anything you can select to solve this. So this is a radial base function assumption. The thin plate The thin plate is I put a plate on there. Then I will try to fit a thin plate. The thin plate depends upon the flexibility of my plate. So the argument is determined by how large the curvature you allow to the surface. Yeah. So if you allow very little curvature, then the plate will be very stiff. If you allow ives very large, then your curvature can be highly variable, be more compliant. Delineal triangulation is that you identify all the maximum, minimum, or maximum, minimum. You connect all the maximum and minimum to its neighbor points by little triangles. After you create this triangle has up and downs, then you try to smooth it. You try to smooth the surface. So that smoothing is also very difficult and time consuming. Not only that, see here along the boundary, it may not be extrema. So it's very difficult to fix the boundary. And after you make all the triangulation, it looks like a little angle like this. It's all little hills and valleys. So using all this method, they have already created many, many different kind of image analysis. And that's, for example, you have a fabric, and you go through this. You look for the small texture, and in this actually is hidden some damage, some blemish. You can actually get it out because using the scale separation, the texture and the background can be separated easily. So using this EMD, you can do this. Yeah. But all of these examples are all implemented by this very expensive, computational expensive method. And many of this method has drawback. For example, when they try to use thin plate, because there are so many points that you have to touch, yeah, many people try to save time by institute a threshold. So if the maximum is less than certain value, I ignore it. Yeah, but that is not fair. If you only determine a maximum value, if a small bump sits on a hill, then that's big enough. You identify it. If a pretty big bump sits in the valley, so the value is still small, absolute value is small, so you ignore it. So that kind of approach favored the large hill. A large hill may have little bump, you get the texture out of that, but the valley you ignore. So this value, because of the implementation, this leaves a lot of argument for how well this two-dimensional will work. But people has tried it, and it works pretty well for many cases. This is one of the example. This is another example. Here, another fabric. You cannot even see these two lines. And then you actually get the two lines out. Yeah. Here is an example. Use delineal triangulation. This is a image of the ocean surface with waves and also with a bottom topography. Yeah. The bottom topography generates some currents, and the current interacting with wave and create a wave change. Using EMD, you can get the background out. This is the bottom topography, and this wave actually becomes much more smooth. Yeah. Here it's an example applied to medical image. This is your original picture, and after you get a mode 1, the highest, smallest scale wave, you can see a lot of small structures. It's not clear here, but you've seen there. Like here, it's almost uniformly gray. Here, you see some contrast, and even in the head, you start to see, and they are actually layered structures. So, the EMD is useful, and it has been applied to this image. This actually is done by the French group in Paris. This was done pretty early, 2003. Yeah. So, image like this. So, this is the original image. I can get mode 1, mode 1 is residual, mode 2 residual, mode 3 residual, and then you can recombine this and get different kind of combination. Here is another thing. When you image, you get this blood vessel, and you look at the blood vessel. The signal is very jumpy. Then you take mode 1 away, and then you try improve the contrast. Yeah, these are all different ways to implement, to use, to apply HHT in image analysis. This application is to use slice. Here, it's some of the surface wave image. This surface wave image is actually created in the tank. The wave propagating this way. Yeah, this is very fine, very high resolution image of the wave surface. I like this surface because this is in my tank when I was working for NASA. This wave propagate, and you can see this wave propagate, and right over here, the water wave surface start to break. Yeah, and when it break, I don't know whether you can see it clear or not. You see here is the structure. That means when this wave break, it create a semicircle shock around the water. I look at the screen; it's very clear. I don't know whether you can see it or not. And not only that, this create another structure right near the crest. The breaking started even more, move forward, and eventually the surface collapsed. This is using a slice. What we did was we cut the surface. This is 256 by 256. So you cut the picture in 256, each pixel, 256, and analyze each line, 260 times, and then put the mode 1 over here. Now you can see the circular circle much clearer than the original picture. Yeah, but the disadvantage of this is that you introduce a lot of streaks, horizontal streaks. So the horizontal streaks you cannot totally eliminate. Part of the reason of the horizontal streaks is actually due to the slight jump, slightly mode mixing across the line. Yeah, and here if we can, of course, at that time we do not have the EEMD. And even if we have EEMD, we will not be able to do it because this I did it way back in 2001, 2002. The computer is so slow. Even for this, we have to wait for the computer to run whole evening. to give us this answer. Yeah. Now, but the nice thing about that is you indeed identify this semicircle shock much clearer than the original picture. And then you look at mode 2. The mode 2, it's more random, but when you look at mode 3 give you a clear structure like this. And this is almost like the two soliton group cross each other. Has a phase jump here. Yeah. This kind of thing, once you see this and you go back to your original picture, you can see the two. Here, it's the cross wave. Here is the shock wave. Yeah. You can, once you get this clearly identified, and you also know that exactly this is the phase IM3, then you know exactly the scale. So 4 and so on. So if you take one simple section of that, the simple section looks like this. The surface suddenly jump and down. So this is one wave, and these are the waves sit in front of the big crest. That is, if we take a section here, this is a big wave. This is many small waves. The small wave actually is what we call the parasitic capillary wave. That means the capillary wave is actually generated by the large wave. The large wave crest pushes the water, and the water wrinkles, generate ripples. Yeah, and these are the ripples that's generated. If the slice, once we generate the slice, you can actually generate a spectrum. The spectrum is actually generated by decompose this into its component, and each of this we can generate a spectrum. This is horizontal distance. This is a wave number. Yeah, this spectrum corresponds to this wave. Yeah, we have a very large crest and have in X direction, large crest and a lot of this high energy oscillation like this. Yeah. So and then we have another crest which correspond to these waves. So in this way, for each slice, you can generate one Hilbert spectrum. We have 256. So this 256, you glue it all together. Then this energy and this energy, this part of energy, will becomes a body. And this body will have density. Yeah. So then that is the 3D spectrum. Actually not 3D. That's the Hilbert spectrum of the 2D picture. Each 1D, one single time frequency, one single time series, when you get the Hilbert spectrum, it's 3-dimensional. Time, frequency, energy. So you have 2-dimensional, you have X and Y, wave number, and energy. It's 4-dimensional. To present this 4-dimensional, you glue it all together, it's a body. This body has different density. Certain part the energy is high, certain part the energy is low. So you get a body of, you have a body of, the Hilbert spectrum actually look like this. Yeah, this is a X and Y direction, and this is the wave number. This is not time. This is actually a wave number. Yeah, and inside this you have energy. This energy actually is isosurfaces. Each surface has the same energy, amount of energy. You can peel this. See, this is for peel at 0.05, and if whoops, I don't have the other. We have peeled this one layer after another after another. You can see how the energy finally shrink to the core. So this is the kind of spectrum that we got. For the other two-dimensional, they cannot produce the spectrum. The reason they cannot produce spectrum is that we do not have the equivalent of two-dimensional Hilbert transformation or two-dimensional quadrature or whatever. We cannot find the wave number equivalency. Yeah. So we stop, all the others we stop. But this one, because it's a water wave, the spectrum actually has a certain meaning. So we had the Hilbert spectrum look like this. So this bidirectional EMD deserves lots of attention in the future development. There are thorny problems that need to be resolved. Yeah. For example, 2D equivalent of Hilbert we don't have. Yeah. All of this are almost solved. In fact, now we can extend Hilbert EMD to multi-dimension. In other words, any dimension we want. Yeah. And basically what we did was by slice and recombination. Yeah. So we do not have enough time. If I started, I would be stopped at the middle of something. Let's call it today. Let's stop it here. Okay. So today we'll stop here. Next time, I will start with multi-dimensional ensemble EMD. So give you a method actually to look at any dimension data. Then we can also do ensemble EMD and get the value and reconstruct the image. And if you want, you can compute the Hilbert spectrum out of it. Yeah. Okay, we'll stop here today. Any questions? Yeah, you will. That's why you have to. That's a very good question. Actually, if I have a sine wave, for example, if a sine wave looks like this, if I cut this way, I get the wave number just right. If I cut this way, I will not get anything. If I cut this way, then I will have a wave number very different from this because it's a projection. So for two-dimensional wave, for two-dimensional slice, we have to think about how to reconstitute it. Even if we cut both x and y, there's still no guarantee that you get the right answer. Because you cut this way, there's no wave. Cut this way, it's wave. So then maybe you say that the wave number here is 0, wave number here it's a certain value, therefore my wave is in this mean direction. That's possible. But then you have to relate each wave number to the same scale. But that's not easy. The reason is suppose I have wave crest like this. Yeah? And if I cut this way, my wave length is this. So my wave number k is 1 over L. It's L1. Yeah. If I cut this way, my wave number becomes L2. So my wave number L2 equals 1 over L2. Wave number 2, wave number 1. It's very difficult to associate this with that number if your wave is more complicated. So it's difficult to match. Once you get this picture and that picture, it's difficult to match. Yeah. So this slice method has its shortcomings. You have to select your direction, cutting direction judiciously. The main direction is that I cut in this direction. Yeah. The wave number the wave number and the resolution actually follow a cosine law. In the direction, 0 direction, you have the best resolution, 1. And perpendicular to it is half pi. Then you have resolution power of 0. Yeah, so it's a cosine law. Next time, we'll show you the different way to do this. Yeah. Actually, we cut both directions at the same time and actually match it right away. Okay? All right. Thank you very much. We'll stop here.